dive, everybody. Get ready to rethink some assumptions because today we're going deep on double descent in deep learning. You know that bias variance trade-off, right?
Absolutely.
Like where if your model gets too complex, it's just memorizing the training data.
Right, right.
That
Instead of actually learning the real patterns.
exactly. Well, imagine a scenario where going bigger actually helps.
Yeah, it's really a fascinating challenge to a lot of the conventional wisdom we've been operating under for years in the field.
Absolutely. The paper we're diving into today is Deep Double Descent, where bigger models and more data hurt. It's by Nick Kieran and others. And it's a really, really fascinating paper. So let's unpack this idea of double descent. So basically, the paper is saying that the relationship between a model's complexity and how well it performs, it isn't always a simple U-shaped curve like we thought, right?
Yeah, definitely not a simple U shape, more like, if you're on a roller coaster and there's a surprise second dip,
Yeah.
you're going down, you think you're getting to the end, and then whoop, down you go again.
Exactly. So as you increase the model size or even just the training time, the performance can actually worsen at first.
Yeah.
Like you said, that error rate, it kind of goes up. But then, and this is the really interesting part, it often starts to improve again.
Right, and that's where this whole idea of double descent comes from.
Exactly,
All right.
exactly. And it's illustrated really well in figure 1 of the paper. If you have the paper open and you want to take a look, it's not your typical smooth U-shaped curve on the graph. There's like this peak in the error rate, right, where the model can perfectly memorize all the training data.
Yes, it gets overconfident for a second there.
It does.
Trips on its own shoelaces,
Yeah.
and then regains its balance.
Exactly.
It's interesting, too, it's not just about the size of the model either, right?
Yep.
Figure 2 shows that the same kind of pattern can emerge, even if you've got the same model, you're just training it for a longer time, more epochs.
Yeah. So it really seems like it's not just about like throwing more parameters at the problem, but like how effectively those parameters are actually being trained, right?
Absolutely. And that's where this paper's introduction of effective model complexity, or EMC, becomes really, really important.
Right.
It's something that, I think is really valuable for anyone out there building ML models. EMC, it's a way of thinking about how confidently your model is using its knowledge, as opposed to just how much raw knowledge it has.
I like that.
You can have a really big model, but if it's not using those parameters effectively, the EMC might actually be surprisingly low.
Yeah. It's like the difference between, a rookie with a huge toolbox versus a seasoned craftsperson who knows exactly which tool to use and when.
Exactly. That's a great way to put it.
Mm.
And the interesting thing is that this EMC idea, it's directly tied to that double descent curve we were talking about, that peak in the test error. Often that's happening when the EMC is roughly the same as the number of training examples.
Interesting.
They call it the critically parameterized regime in the paper, which sounds kind of intimidating.
It does.
But really, you can think of it as this point where your model complexity and your data size are in this like delicate dance-off with each other.
I see. I see. Now you might be thinking, okay, this double descent thing sounds interesting, but it also sounds like maybe something those researchers cooked up in a lab somewhere. But it gets really interesting when you see just how widespread this phenomenon might actually be in the real world. So how widespread, I rest, is this in the real world?
Well, they really didn't hold back in this paper.
Right.
They didn't just look at one specific type of model or data set. They said, all right, let's throw the whole kitchen sink at this thing. They looked at convolutional neural networks.
Those are popular.
Yeah, ResNets, even
Yeah.
those super trendy transformers.
Right. Everyone loves a transformer.
And they tested it across a bunch of different data sets too,
Sure.
SciFar 10, SciFar 100. They even looked at some language translation tasks. And they didn't just stop there, right? They even tried using different optimization methods like your stochastic gradient descent, Adam.
Yeah, the bread and butter.
Yeah, exactly. Exactly. Your tried and true methods. And guess what? They found evidence of double descent in pretty much every single one.
Wow.
Yeah, it wasn't just this niche thing they stumbled upon. It seems like it might be this hidden pattern that's been lurking beneath the surface of our models this whole time.
That is so interesting. So for, our listeners out there who are building models right now, I mean, this could be for anything, right? Medical diagnoses or, financial forecasting, whatever it is.
Absolutely, yeah. Any kind of machine learning model.
This research has some really, really important takeaways, right?
Yeah. Yeah, I think a really big one that we kind of touched on earlier has to do with the size of your data set.
Okay.
And this is one of those things that might sound a little counterintuitive at first, but bigger isn't always better.
Oh, interesting. Okay.
Yeah, there are actually scenarios where if you increase your training data, you can actually make your model's performance worse.
Really? I thought more data was, our best friend in this business.
You would think so, right? More data, more better. But if you look at figure 3 in the paper, they actually show an example of this happening. It's in a language translation task with a transformer model.
Wow.
And it kind of makes sense if you think about it. It's like adding more ingredients to a recipe without adjusting the cooking time, right?
Right.
You might just end up with a mess.
Right.
So it's not that more data is inherently bad. It's that we need to be aware of how it interacts with this whole double descent phenomenon.
Hmm.
We may need to rethink our training methods when we have more data, and adjust our expectations accordingly.
Yeah, that makes sense. So it's not that the old rules are totally out the window.
Right.
It's that with these really, really complex models
Exactly.
that we need to kind of, update the rule book a little bit.
Yeah, the old rules of thumb don't always apply in this new world that we're in,
Yeah.
with these really complex deep learning models. And speaking of things that kind of challenge our assumptions, one of the things they found was that this double descent effect was most prominent when they had noise in their training data,
Hmm.
and specifically label noise.
And you don't just mean, like a couple typos here and there, right?
No, it's a bit more fundamental than that.
Yeah.
This goes back to this whole idea of model misspecification.
Yeah.
Those times when the assumptions that our model is making about the data don't quite line up with, the messy reality of the data we're actually feeding it.
Right, like trying to fit square pegs in round holes.
Yeah, exactly. Exactly. You got it.
And let's be real, like in the real world, how often is our data perfectly neat and tidy?
Oh, never.
No.
Never. I mean, even with the best data cleaning, the best pre-processing in the world, there are always going to be these little mismatches between what our model thinks the data should look like and what the data actually looks like.
Right.
And that's where this idea of misspecification comes in, right? It could be subtle biases in the data. It could be these hidden correlations that we haven't accounted for. It could even just be the fact that, our models, they're really just simplified representations of this incredibly complex world.
Right.
Right?
Right.
It's like trying to summarize, like a whole novel with just one sentence.
Yeah.
You're inevitably going to lose some important details along the way.
Exactly, exactly. So it sounds like this double descent phenomenon, especially when you start throwing in things like label noise and model misspecification,
Yeah,
it kind of reveals like this whole nother layer of complexity
absolutely.
that we need to be aware of when we're, building and training these models.
Definitely.
But before anyone listening out there panics and, chucks their really complex models out the window.
Yeah, don't hit that delete key just yet.
Yeah. I think it's important to remember that this research isn't trying to say that complexity is bad, right?
No, not at all.
It's really about, understanding this new terrain that we're in. It's about understanding this new terrain that we're in, with deep learning. So instead of freaking out when we see like, a little bump in that error rate or shying away from using those bigger models.
Yeah. Don't be afraid of the complexity.
Exactly. I think this research is like a big flashing sign telling us, hey, pay attention to things like effective model complexity, that EMC we were talking about.
Right, right. And don't forget about that critically parameterized regime either.
Exactly. Especially, like you said, when we're dealing with noisy data, which, let's be real, is most of the time.
Yeah, pretty much. It's rare to find a pristine data set out in the wild.
Exactly. And I think it's interesting, too, because for so long we've been told more data is always the answer. Just throw more data at the problem. But this research suggests
It's not always so simple, is it?
it's not. And it makes you wonder, too, about like those early stopping techniques that we use, right?
Oh, yeah.
Like, are we actually masking some of these effects of double descent by like hitting the brakes too early?
Yeah, it's possible, right? Like,
Oh.
we're so used to hitting that stop button as soon as the training error plateaus or maybe even starts to creep up a little. 'Cause we're so afraid of overfitting.
Okay.
Right, exactly. Overfitting. Sound the alarm.
Yeah, exactly. But maybe this research suggests that we need to like recalibrate those alarms a little bit,
Maybe those alarm bells are going off a little too early.
Maybe. Or maybe like this points to something even more fundamental about the way these really, really complex models work that we just haven't quite grasped yet,
Yeah. There's still so much we don't know about deep learning.
It's kind of humbling, isn't it, to think about that?
It is. It
Because
really,
they come so far,
right.
but there are all these, like, nuances and things we're still uncovering.
It's like we're still just scratching the surface.
Exactly.
Yeah.
Which is really exciting too, right? It means.
Absolutely. It
Doesn't.
keeps things interesting.
Yeah. It means, like, this paper we're talking about, it's not just like, the end of the story. It's really opening up like a whole new avenue of questions and research to be done.
Yeah, and one of the big ones that really jumps out to me is, we're saying that this double descent phenomenon seems to be pretty common.
Right.
So then why haven't we noticed it more in, practical applications? Like, why wasn't this something that was like really obvious to people who are out there building these models day in and day out?
That's such a good question. It's like, this elephant in the room, like you said, that maybe we're just now starting to really see.
Yeah, exactly. And maybe it is, like we were saying before, maybe those common practices like early stopping, they've just been masking it this whole time.
Yeah. Or maybe there's something like more fundamental about it that we're just missing, you
Yeah,
know?
still so much to explore.
It's like, you think you know this castle,
Yeah,
and then you discover like a hidden passageway. You're like,
yeah.
"Whoa, where does this go?"
Right. Time to get out the flashlight and do some exploring.
Exactly. And that's what's so cool about this field, I think, is that there's always something new to discover.
Yeah.
So to all of you listening out there, who are deep learning explorers yourselves, keep an eye out for this double descent thing in your own work. And don't be afraid to experiment. Question those assumptions that we've all kind of come to accept. And most importantly, like, share what you find, because you might be the one who cracks the code on this whole thing.
Exactly. We need all the bright minds we can get on this.
And that is a wrap on our deep dive into double descent. This is really fascinating stuff. Hopefully it'll help you train some even more awesome models out there. We'll be back next time with another thought-provoking topic. Until then, happy training, everybody.